Okay, it's Wednesday's lecture here. We're Physics 1151. It's late at night, so I'm trying to get through this. So today we're gonna cover Faraday's law and induced fields. And if you look here, we've got a picture of the electromagnetic spectrum, including light, and we have electrical generators. And what do these have in common? Well, they both have in common that they rely on the changing electric and magnetic field, or the changing magnetic field inducing an electric field, and a changing electric field, in this case, inducing a changing magnetic field. And so we started to go through this with the concept of flux and Lenz's law, and we're going to generalize this today to Faraday's law. So we're going to do a quick review of magnetic flux and Lenz's law. Then we're going to discuss Faraday's law, and then we're going to get into the electric fields that are created by the time-varying magnetic flux, and how this leads to electromagnetic waves. I'll be posting the homework on this Saturday morning at some point. Like I said, you don't need to turn it in, but the solutions will be posted, and you are responsible for the material on the final exam. So come into office hours to go over any problems of difficulty. So as a quick review, recall that Michael Faraday back in the 1800s did some experiments, and he observed that if you change the amount of magnetic field going through a loop of wire, that you can get a current induced in the wire. Okay. So then we defined what this amount of magnetic field means through this quantity called the magnetic flux, right? And the flux is just the dot product of the magnetic field at the location of the loop with the area of the loop. Remember, we made area a vector whose magnitude is the area of the loop and whose direction is perpendicular to the loop. And so you can also write that as B times A times the cosine of the angle between B and A. Basically what this theta is if you start with the loop perpendicular to B, so it's flush with the field, and you tilt it by some angle theta with respect to the field, that is the angle with respect to the loop. Okay. And so if you have a constant field, it's B dot A. If you have a magnetic field which varies over the loop, then you have to integrate that, and it becomes B dot dA. Okay, so this is all a review from the last lecture. So if you look at the equation that the flux is equal to B times A times the cosine of the angle between them, and remember that it's only changes in flux that change with time that give rise to the current. There's three ways you can change the flux with time, right? You can change the magnetic field with time. So in other words, a time-varying magnetic field going through the loop. If it gets stronger or weaker or oscillates in time, that'll induce a current. You can change the area of the loop with time, and we observed that with motional EMF in the 2 lectures ago. Or you can also change the tilt angle theta. In other words, you rotate, one example is you rotate the loop with respect to the magnetic field. All of these can generate a changing flux, which gives rise to the current in a loop. So we calculated flux, then we discussed if you give a change in the flux through a loop, Lenz's law is used to give you the direction of the induced current. Okay, and remember with Lenz's law, it says that the direction of the current is such as to oppose any changes in the flux. Okay, so for example, In this example we did from last lecture, remember the field lines are going down through the loop from the North Pole, and if we're pushing the magnet toward the loop, the downward flux is increasing, right? So now we want to calculate the direction of the current. So because the flux downward is increasing, the magnetic field produced by this induced current will be upward. It'll be opposing. It'll be in the direction opposing this increase in flux, so it will counteract it. So you stick your thumb in the direction of the induced field, which is upward. You curl your fingers, and your fingers will curl counterclockwise, and that gives the direction of the induced current. Okay. Then if we do another example here, where you have the downward flux through the loop decreasing, for example, we're moving the magnet away from the loop, then this induced current will be such that the magnetic field will reinforce this downward magnetic flux because it's decreasing, so it doesn't want it to be opposed, doesn't want it to change. So you point your thumb downward in the direction of the induced magnetic field, and you curl your fingers and you curl them clockwise, and that gives the direction of the induced current. And so in summary, Lenz's law, to get the direction of the current, you first have to know the direction of the field, the applied field going through the loop, and it was downward here and downward here. Then you determine if the flux is changing. If the flux is increasing, the induced magnetic field points opposite the applied field to counteract it. If the flux is decreasing, the induced magnetic field points in the same direction. Okay, and so, for example, here the downward flux was increasing if we're pushing the magnet toward the loop, so the induced magnetic field is upward. Okay, now you point your thumb up, curl your fingers, right hand, and that gives you the direction of the current. Again, over here, the downward flux is decreasing, so the induced magnetic field is in the same direction, downward. Point your thumb downward, curl your fingers clockwise. Okay, so this Lenz's law gives you the direction of the induced current in the loop. However, it doesn't give you the magnitude of the loop. Okay, and this is where we need, or the magnitude of this current, and this is where we need Faraday's law here. So now if you remember back from your days of electrostatics, to actually get a current in a loop, to push current through the loop, through a wire, you need an electric field, right? The electric field has to push the current against the resistance of the wire through the wire. And if you have to induce a current, you need an electromotive force, right? Or an EMF must be generated in the wire. Okay, we already derived this for motional EMF, the conductor moving in the field. Now we're going to generalize this, okay? So Faraday's law basically generalizes this induced current to any change in flux, changing magnetic field strength, changing area, changing angle. Okay. And so this was equal to the EMF, the electromotive force induced in the loop, divided by R. Okay. Faraday's law simply says that the EMF is equal to the magnitude of the time variation in the flux. So it's the change in flux over the change in time. In other words, it's equal to the rate at which the flux is changing through the loop in time. Okay, and this gives you the magnitude of the EMF. Okay, and then the direction is such as to drive the current in the direction given by Lenz's law. Okay. So Faraday's law just says that the mth created is the magnitude of the time rate of change of flux. Then you plug that in to Ohm's law, and you get that the current is equal to the mth divided by R, and you get the induced current. If you have an N-turn coil like a solenoid, then you need to multiply the change in flux in each coil by N to get the total mth. So you can get a large mth induced in a coil if you have many turns. So now what we're going to do is we're going to plug in what the flux is. The flux is equal to B times A times the cosine of theta. And so the mth is just the time derivative, or the rate of change of the flux. Okay? And if any of these change in time, B, A, or theta, then you're going to get an mth through the loop. So let's go back to our motional mth problem that we did back 2 days ago. So here we have the loop. Remember, here we had the conducting bar, the conducting U here, and then we had the bar. Remember, the bar was moving. We pulled it with velocity v, and what we were doing here is we were increasing the area of the loop with time, right? And so if you look back at this equation, if the area changes with time, you will get an electromotive force which will drive current around the loop. So let's calculate this here. So here we've got at the area of the loop at some time t has a width L and a length L and a width x. Okay, and here's your conducting bar that's moving. So this forms a loop. And so the mth is equal to the rate at which the flux is changing in time, okay? And here you have the area of the loop, which is perpendicular to the screen, is in the same direction as B, and so the angle between the area and B is 0. So cosine of 0 is 1, and we multiply the area, which is just L times X, with the magnetic field strength B, times the cosine of 0, which is 1, and you get that the flux is equal to length times width, which is the area, times B. Okay. Now we plug that in for the flux, and we take the derivative of the flux with respect to time. B is not changing with time, so we can pull that out of the derivative. L is not changing with time, we can pull that out of the derivative. And then dx dt, the change in x with time, is just the velocity. And so you get that the mth is equal to the magnetic field strength times L times the speed. Okay? And this is the same result that we got earlier using the electromotive force, the separation of charge, but we derived it using Faraday's law as the time derivative of the change in flux. Okay, and this is a more general case. Okay, so anytime we have flux that's changing, we take the derivative with respect to time, and we get the mth. Now, which direction is the current going to be in? Okay, well, the flux is going down into the screen, and as the area gets larger, meaning we pull the loop to the right, this bar to the right, the downward flux is increasing, okay? So the induced magnetic field is going to point up. It's going to point opposite the direction of the downward field. And if it's pointing up, you point your thumb out of the screen, you curl your right hand, and the current induced is counterclockwise, and it has a magnitude equal to B times the length of the wire times V. Okay. So this is using Faraday's law to calculate the induced EMF. Okay. And if this has a resistance R, this conductor, we would get the current by the EMF over R. Example 2 is a somewhat similar example. I'm going to leave that to you. Here's the solution to work out on your own, and we can go over that in office hours or in the synchronous lecture next Monday. Here's a little different example, and this is going to lead into our next topic. So I want to go into this example 3. I want to go over this one. So now you have a solenoid, and suppose it has 1,000 turns, so a coil of wire, and the turns are all coming out of the screen toward you. Okay, so you're looking right down the axis of the solenoid. And if you remember from the last chapter, the magnetic field of the solenoid inside is along the axis of the solenoid. So inside it would be pointing into the screen. Okay? And now you have 1,000 turns, and we know the diameter. And let's suppose that we have a magnetic field that varies with time. So it starts at 0.1 Tesla, and in 10 milliseconds it increases linearly to 0.3 Tesla. And so the question is, what is the EMF, the electromotive force, or in other words, the potential difference between the ends? What is the EMF induced in this coil? Okay, so here we have to apply Faraday's law, right? The EMF is the change in flux over the change in time, but since it has n turns, we need to multiply by n. This is for a single turn. Okay, and then we plug in that the flux is B times A times the cosine of theta. Okay, remember where theta is between the area, the angle between the area, which is perpendicular to the loop, and the field. And again, in this case, the area vector is perpendicular to the loop, which is along the direction of the field. So the angle between the area and B is 0. Cosine of 0 is 1. Okay, so that's 1 and it's constant. The area isn't changing, so we can pull the area out. And then the equation for the EMF is the number of turns times the area times dB dt. Okay. Now we know we can calculate the rate at which B is changing because it goes from 10.1 Tesla to 0.3 Tesla in 10 milliseconds. So that's a change of 0.2 Tesla divided by 0.01 seconds. Or in other words, the magnetic field is increasing at a rate of 20 Tesla per second. Okay, so we plug that in for dB dt. We can calculate the area because we know that the radius is 0.05 centimeters. So you plug that in, and the area is 7.8 times 10 to the negative 5 meters square. So you plug that in for A. You plug dB dt as 20 Tesla per second. You multiply by 1,000 turns, and you get an electromotive force in EMF of 1.6 volts. Okay, so that's the electromotive force pushing the charge around the loop. It's basically pushing the current around the loop. Okay, so in this case, it was B that was changing, and you had the area constant and the angle constant, whereas in the previous example, B was constant and the area was changing. So here we've got the figure here, and so the same as last time. So you have a solenoid again with the magnetic field pointing into the page, into the board, and that's going to, we saw that that is going to induce a current going counterclockwise around the loop, right? And if there's a current, that corresponds to an electromotive force force, right? So the electromotive force given by Faraday's law is what's going to drive that current. And the electromotive force, therefore, since that's pushing charge around the loop, corresponds to some electric field E, which everywhere must be along tangent to the loop, right? So this electric field that's created by the changing magnetic flux is giving rise to a current around the loop. Okay, so what this means is that if you have a changing magnetic field through a loop, that will induce an electric field whose direction is circles, since it's tangent to the loop at every point. So that induces a circulating electric field. Okay. Now, it turns out that even if we remove the wire, so suppose we actually remove the wire from the field here, but we continued to vary the magnetic field with time. Okay? You wouldn't get a current because you don't have a wire, but you still would get a circulating electric field whose directions are circles surrounding the magnetic field. Okay? And this is just a simple consequence of the changing magnetic field. So even without a wire, you can't get current if you don't have a wire. There's no current. But you still will get a circulating electric field that results from a changing magnetic field. Okay? So now what we see is we have a new way of creating electric fields. Okay? Remember from chapter 25, electric fields were created by charges. Well, now we see that a circulating electric field, where the field lines are circles, is created by a magnetic field which changes with time. So changing magnetic fields induce electric fields whose field lines are circles. So what we want to do now is get an expression to calculate the magnitude of this induced electric field. Okay, so if we go back to chapter 25, recall that we define this potential difference as the change in potential energy per charge, or the negative of the work done by the electric field per unit charge. Okay, and that was equal to negative E dot ds. So in this case, this circulating electric field cannot be associated with a potential because the work done by it around a closed loop is not zero. So we can't define a potential, but we can associate this M, this electromotive force, as the negative work per charge. And that's equal to E dot ds. In this case, it's around the loop because the electric field lines are circles. Okay. And we know that this EMF is also equal to the time derivative of the change in flux, the magnitude. Okay. So we now have an equation that E dot ds around this closed loop is equal to the time rate of change in flux. That's the magnitude. Now, in many cases of interest, including this, you see that B is perpendicular to the loops, okay, which means if you make area perpendicular to the loop, remember, so B and A are in the same direction, so cosine of 0 is 1. And if the area of the loop is constant, then Faraday's law says that the integral of E dotted with ds around the loop is equal to A times dB dt. So in other words, a magnetic field that changes with time, in other words, dB dt is not zero, induces a circular electric field around the loop. Okay. So this, remember, so here I'm kind of summarizing this. So Remember, you have a time-varying magnetic field induces a circular electric field. By circular, I mean the field lines are loops surrounding the loop. Okay, and this electric field is induced whether there is actually a physical wire loop here present or not. Even if we remove the wire, you will still get a circulating electric field, which is a consequence of the fact that the magnetic field is changing in time. Okay, and so now we have a second way of creating an electric field. Remember, the first way is by charges create electric fields. Now we found that a changing magnetic field will create electric fields. Okay, without charges present, you don't need charges. Both of these fields, although from different sources, will exert forces on charges that are present in the fields, right, which is equal to Q times E. So here's an example, okay? Suppose that the electric field amplitude is constant around the loop. So we're at some radius r from the center of this loop. And in this case, E dot ds, if we integrate around the circle, the electric field everywhere is parallel to ds. So E dotted with ds is E times ds times cosine of 0, which is E times ds. And we're going to integrate this around the circle. Okay. Well, if E is constant at all points, we can pull it out of the integral. And ds around the circle is just the circumference, which is 2 pi r. So we get that the left side, the mth, is just E times 2 pi r. Okay? That must be equal to the time rate of change in flux, and if the area is constant, and this is equal to a dB dt, you plug in a as pi r squared, the r's cancel, and you get that the magnitude of this electric field is r over 2 times the magnitude of the change in time of the magnetic field. So in other words, the faster the field is changing with time, the larger the electric field that is induced circulating around the magnetic field. Okay, so what have we learned so far today? Well, we've learned that if you have a time-varying magnetic field, in this case time-varying pointing into the screen, it's changing with time, that this will give rise to an electric field whose direction are circles surrounding around the, or circulating around the magnetic field. Okay, and this electric field is real. It exists whether or not you actually have a loop of wire here. Right? And if you have a loop of wire, then this circulating electric field will be the electromotive force which pushes the current through the wire. Okay, but regardless of whether any wire is physically here, a changing magnetic field in time produces a circulating magnetic field. Now, James Clerk Maxwell, who only 2 years after getting his undergraduate degree wrote a paper, and in his research paper, he correctly postulated that if a time-varying magnetic field can induce a circulating electric field, then a time-varying electric field should be able to produce a circulating magnetic field, the symmetry of the electric and the magnetic fields. Okay, and in his field, it was not to oppose the change in flux, so there wasn't a minus sign, and so this went in the other direction. But he still postulated that the time-varying electric field could also produce a magnetic field. Okay, and it turns out that Maxwell was right. And he did this without any experiments. He did it solely using mathematics. So for those of you who think that You don't need math to do physics. Maxwell would beg to differ. And so one consequence of this is that Maxwell, based on this, correctly predicted, using electromagnetic theory, the existence of electromagnetic waves, which we see as light, or they're microwaves, or infrared radiation, or X-rays. And so Maxwell correctly predicted the existence of electromagnetic waves from electromagnetic theory. Okay? And what these waves are is, you start off, and if you have a changing electric field, that produces a changing magnetic field, and a changing magnetic field then produces a changing electric field. Changing electric produces changing magnetic, and these two continue to feed off each other as they propagate away from the source, and this gives rise to electromagnetic waves. Okay, so you couldn't predict electromagnetic waves using electromagnetic theory without the existence of this term right here, which says that the changing electric field induces a magnetic field. So that was never known before until Maxwell, based purely on mathematical grounds, predicted it. Okay? Now, to make it even more amazing, Maxwell even predicted, using electromagnetic theory alone, the exact speed that these waves travel at, 3.0 times 10 to the 8th meters per second, which we call the speed of light. And so Maxwell predicted, using his equations of electromagnetics, that the speed of light, c, is 1 over the square root of epsilon naught times mu naught. And if you remember, epsilon naught was that constant, the electrical permittivity in Coulomb's law, and mu naught, this one with epsilon naught, was 8.85 times 10 to the negative 12, and mu naught was the magnetic permeability, which was in Biot-Savart law, and so that was 4 pi times 10 to the negative 7. And when you plug these two values in, you take the square root, you hit the inverse, magic, you get the exact speed of light in vacuum. So Maxwell, using mathematics alone, predicted the existence and the exact speed of electromagnetic waves before this was ever experimentally determined. So let's stop and do it. There's a short little video on electromagnetic waves, which is very good.
What is electric and magnetic about light? To answer this question, we need to talk briefly about electric fields. But don't worry, it's going to be short. A charge placed at a given point in space will generate an electric field around it. The strength of that field at a given position is represented by a vector. The magnitude and the direction of this vector represent the magnitude and the direction of the force that would experience a positive charge of 1 coulomb placed at that position. Now, imagine a metallic bar and focus on one of the electrons in the bar. This electron creates an electric field around it. Then, connect the bar to a source of alternative current. The electron will move back and forth in the bar with the current. It will oscillate. And so will the direction of the electric field the electron generates. This idea is a key point. If you look at how the y component of the electric field strength vector changes with time, it is oscillating, and it can be represented by a beautiful cosine or sine curve. In the second part of the 19th century, Maxwell showed that a changing electric field generates a changing magnetic field and vice versa. So the oscillation of an electric field always generates a magnetic field that oscillates too. Let's go back to our electron. Suppose now that I choose for the alternative current a frequency of oscillation of 10 kHz. This means that the electron oscillates 10,000 times per second. And so does the electric field it generates, as well as the induced magnetic field. Imagine now that I place another metallic bar in the oscillating electric field. The electrons in this bar will feel an oscillating force. Yes, they are in an electric field, so they feel a force. They will start to oscillate too. What we did here is we transmitted a signal through space. This is how radio works. Yeah, we have two antennas. The first bar is emitting the signal. The second bar is receiving the signal. When the oscillating electromagnetic field is generated by the first bar, it propagates through space at the speed of light. Yeah, the oscillating electromagnetic field is what we refer as an electromagnetic wave or EM wave. And it is also more commonly referred as light. For example, let's increase the frequency of the alternative current up to 10 trillion Hertz. The electron in the bar will oscillate at 10 trillion Hertz, and so will the electric field it generates. The resultant EM wave is now infrared radiation. Let's increase the frequency a little more, up to 1 quadrillion Hertz. The metallic bar starts to glow now. It emits visible light. Did you enjoy this video? Then like.
So the video there showed how electromagnetic waves are produced. Okay, now for radio waves, that's how they're produced. Okay, you have an antenna, and you jiggle. You have electrons. You have an alternating current going up and down, and so your electric field is changing. As the charge sloshes up and down, the electric field direction changes. And if your electric field direction changes, it generates a magnetic field around the loop. Remember, a changing electric field in time generates a circular magnetic field that circulates around the loop. Now you've got a changing magnetic field with time, and that induces an electric field, and this disturbance propagates away each time that the charge goes through one full cycle from top to bottom, back to zero. This wave goes through one cycle of a sine wave propagating outward. So every time, for every one oscillation of the electron, you get one sine wave of the wave. The wave has propagated some distance, c, the speed of light, times t, outward. Okay? And so these electric and magnetic fields, they change and they feed off one another, and you generate radio waves. Okay? And then these radio waves can jiggle the electrons in a receiving antenna, and that will generate a current, and that's a sine wave too, and you detect the waves then. And these waves travel away from the source at a speed of 3 times 10 to the 8th meters per second, which is the speed of light in vacuum. Okay? And depending on the frequency of this oscillating charge, at very low frequencies you get radio waves with very long wavelengths. Then if you get into wavelengths that are on the order of a centimeter to a millimeter, or frequencies of a few gigahertz, you might have heard of the 5G network. 5G means 5 gigahertz is the frequency of the electromagnetic waves. Now you're in the microwave region. If you jiggle the electrons even faster, you get infrared light, and then visible and UV, and X-rays and gamma rays. So all of these different wavelengths, all these different parts of the spectrum, all correspond to oscillating electric and magnetic fields. They just have different wavelengths and different frequencies. And so what we've seen today is that Faraday's law, which simply says that a circulating EMF is induced by a change in magnetic flux, that gives rise to a host of phenomena, along with Maxwell's assertion, that gives rise to light, and Faraday's law gives rise to electrical power generation, and a whole host of other phenomena that we're going to be getting into tomorrow in our last lecture here. So what should you be able to do here? Well, you should be able to state Faraday's law, the equation, and say it in words, what it means, and you should be able to apply it to relate the induced EMF and the current in a wire loop. If there is a loop, remember that current is the EMF over R. So if you're given various changes in flux, like if the area changes or the magnetic field strength changes, you should be able to calculate the change in flux, use that to get the EMF from Faraday's law, and then divide by R to get the current. Okay. Now to get the direction, you should be able to use Lenz's law to get the direction of the currents. You should be able to do that. You should be able to calculate the magnitude of the circulating electric field produced by the time-varying magnetic field. And you should be able to explain how electromagnetic waves are produced. Okay, so tomorrow, Thursday, is going to be our final lecture of the course. Remember that next Monday through Wednesday, we're going to have a couple days of, I'm blanking here, couple of rest days because you didn't have a spring break. So you can use those to get caught up in the class, to come into office hours, and to get ready for final exam. Wellness days, I'm sorry, now I remember. So with that, I am going to sleep, and we'll see you tomorrow.